to record this as well. All right, welcome everybody who is watching and who is currently present. Nice to see you here today. Might get some more people later down they realize we're going on, and when they do, we'll welcome them as well. So firstly, we're going to go and look at what does the FE handbook look like for electrical and computer engineering, or in this case, today's topic, which is electricity and magnetism. As I said earlier, it's the electricity and magnetism section is actually under electrical and computer engineering. So when I was looking for it before, I looked up electricity and magnetism in the find, and it wasn't finding anything. Like, huh, strange. So it was actually under a different name than I expected. So that's one thing to keep in mind. So we're going to quickly go through, just scroll down through the stuff we got here. We have the electrostatics, force between two point charges, force point charge I, or 1, 2, however many you have. Permittivity, free space of air, we have that constant here as well, good stuff. And basically this goes over the main line of electrostatics, which deals with point charges, charges on spheres, charges on cylinders, magnetic fields as well, voltage, current. Well, that's more of dealing with circuits. You don't really see too much potential difference in electrostatics, but it is still there. E equals voltage over distance, which is the E field. If you know the voltage, you can get the E field with the distance. Current as well, being the derivative of the charge, you get current. And with that, it's basically a moving charge. It's also pretty important, especially when we get into the DC circuits. We have magnetic fields, a little more complicated. Might not see too many problems with magnetic fields, since they do kind of require a bit more calculation than what might be reasonable for the exam. All right, we got a force on a current carrying conductor. Force equals IL cross B. Again, we have a cross product because of the nature of the magnetic field. L, the length vector of this conductor. So when we get asked something about a conductor, we can just go and search conductor up here, and we'll get some of this stuff, and it'd be nice to know. Oops, induced voltage. Is this a surface integral? And again, pretty rarely we will have to do complicated integrals on this exam, since it does take a lot of time. And if you find a problem that does ask you to do something, unless you're really good at what it's asking, you know exactly what to do, it's more recommended to maybe come back to that problem at a later time. Resistivity, we'll be looking at a resistivity problem today. We have the resistivity is equal to rho L over A, where rho is the resistivity at initial temperature. Alpha is the temperature coefficient, or sorry, the rho in that problem is defined by this. R can be defined by this as well for metallic conductors. But typically, if you have rho length and some sort of diameter or radius, we can get the resistivity of a conductor. Okay, now we're going to be getting into DC circuits. We're also going to be looking at those today. Resistors in series and parallel. Series, just add them up. Parallel, you're just going to add the inverse of all of them, and then inverse that thing one more time. Or you can use the simplified version, whichever you like better. Power absorbed by a resistive element. Power equals voltage times current, or V squared over R, or I squared R. Any one of these will work depending on what you have. Some might be easier, some might not. All right, Kirchhoff's law, we got loops. Voltage rises is equal to the amount of voltage drops. That one's going to be necessary for one of the props as well. And Kirchhoff's current law for closed surfaces is the current in is equal to the current out. That one's pretty straightforward, similar to the node rule, where you have I1 coming in and it splits into two. You can have I1 equals I2 plus I3 sort of thing. We have the source equivalence, sources and resistors for a circuit, if you kind of cut off one of the sections that would complete the circuit, you can get a, I'm not sure if I'm going to pronounce this correctly, but the Venin equivalent. You can get the equivalent resistance using the voltage of the source and the current that you would have at the break. Not sure if you can see my mouse or not, but if not, I will highlight things. Okay. We have also a Norton equivalent circuit, which is very similar to the Venin. Only this one can be used. Actually, it's kind of pretty much the same thing, only your voltage source might be alternating. So it depends on the circuit you're looking at. Capacitors and inductors, another important factor. We may look at some of these today as well. Charge and voltage relationship are shown here. C equals QC of T divided by little vC of T, which basically we can get CV of C of T. CVC of T equals to QC of T. And which parallel plate capacitor, which are the most common, probably the only ones we'll see on this test. We have a epsilon A over D is C. We may have to manipulate some of the equations like that to get what we want. Where this is a different permittivity constant than epsilon naught. This is actually going to be ER of epsilon naught, where ER is the relative permittivity. That's where that would come from. And inductors, inductor energy, and current voltage relationships are shown in the next. Continuing on, some more inductance terms. Coil wraps Faraday's law to get the voltage current relationships. If you're a mechanical engineer and you've taken classes in modeling and modeling of dynamic systems, you might have recognized some of these. For when you do modeling of circuits, you have to implement VL and IL depending on your circuit. When we get to that, we'll be looking at that as well. Inductance, capacitors, inductors in parallel and series. These are a little different. Basically the opposite of resistors. Capacitors in series will be 1 divided by, well, basically it's the 1 over the inverse of all of your capacitors. And parallel, you basically just add them up linearly. Inductors will act similarly to resistors, where the series is, you just add them up linearly, and the inverse adding is for parallel. Okay, so now we have AC circuits and rotational machines. We will probably not be doing any problems on those today, since personally for me, I'm not super familiar with that material. It's not something that I went over in depth in my schooling, and now that I have enough time to really kind of learn it on my own. So we're just gonna go through these really quick. If you're familiar with this, that's good. You have a leg up. All right, DC circuits, maximum power transfer versus an AC circuit. After you have the Venin equivalent circuit. RC and RL transient circuits. Yeah, these are another thing that you probably would get asked be a conceptual problem on stuff like this, maybe not calculational, since the calculations might take a while. Resonance, series resonance, parallel resonance, and then AC power, we have complex power. Balanced three-phase, three phase systems. There could also be problems conceptually for this as well, where you would need to know what VL is for a wire, for a Y, sorry, or just know the different formulas that you can use, and it might ask you to recite one of them. Transformers, not too familiar with transformers, but they do have that in here for the information. Transformer designs. And rotating machines. Rotating machines is the next big topic that they could ask questions on. Synchronous and asynchronous machines. We have power developed in a synchronous machine, max power, induction machines. A lot of stuff here. Armature, again, if you took 376 at CSULB, you may have seen stuff like this with these before, though never really got too in depth in it. Transmission lines, difference equations. All right, digital signature post. Okay, so now it looks like we're kind of getting into computer engineering stuff. So at this point, a lot of this may not necessarily be applicable to what we're dealing with. So we can probably stop here and we can get into some problem solving. Yeah, okay. Unless you're a computer engineering major, you will probably not use a lot of these amplitude modulation, double sideband modulation. Some of this looks familiar from controls, but you may not need it for a mechanical test. Okay, let's go back here. Okay, we're going to be starting with some electrostatics. This is a problem that is asking for the distance between P and the left charge. And it's defining P as a point where there is zero electric field between the two charges. Okay. Well, first thing I should ask is, do we know what the equation for an electric field is? If you want to answer, feel free to. If not, I can write it down. Let me move this out of the way. The equation for the electric field, what, K, or we can do 1 over 4 pi epsilon naught. Times our charge Q divided by R squared. And we're going to be in whatever direction, R hat direction. But for this one-dimensional case, that's not entirely necessary, but put it there just, oh wait, we don't need it, it's okay. So this is the equation for the equation of the electric field. How can we find out what that X is using this equation with both of these charges? Because charge 1 and charge 2 are both going to exhibit an electric field, right? But the electric fields tend to be zero, or they may cancel out at this point. So let's see if we can come up with an equation to solve for that distance X. We know that at this point, the E field of the left charge and the E field of the right charge must be the same, because they must cancel out in both directions. And there can't be an E field because it's stated in the problem that there's zero electric field at that point. So what we can do, we can have E1, so left charge, equal to E2, or maybe negative E2, but I don't think the sign matters in this case. So if we have, I'm going to change this into K so we can write less. So we're going to have K Q over R squared. And what is this R squared? R squared equals to KQ over the R squared for the 0.003 Coulomb charge. So this is going to be what? 10 minus X squared. I guess I should call this R squared X squared. consistent. Come on. I don't like that. Really want me to reselect. Drawing tablet issues. Gotta love this. Just have the. No, not that. Do excuse me for this. This is my first time using this tablet for this. A drawing tablet to make writing easier. I'm not sure. It just really likes the eraser. I choose that, and I choose this color. Do you want me to let me draw? That's not drawing. Okay, there we go. I guess it didn't want me to change this R, so I'm just gonna make this R an X. X squared equals KQ over 10 minus X squared. Because if we look this distance here, this is gonna be 10 minus X, since it's gonna be this distance minus, or the whole distance minus this section right here. So we're gonna have that here and that there. Okay, let's make this Q1, Q2. First off, we can see that these K's are going to cancel, which is nice. We don't want to have to deal with things we don't need. Extra terms gone is nice. We want to solve for X. For X, Q2X squared equals Q1 times 10 minus X squared. This is going to result Q1 10 Q1 minus Q1X squared equals Q2X squared. Squared times Q2 plus Q1 equals 10. What Q is this? This is Q1. And eventually we'll get AX squared plus 10X. I missed an X somewhere. This is going to be 10 minus X total squared equals 3X squared, because it's going to be Q2 divided by Q1. And then this, if we FOIL that out, we'll get X, not X2, but X squared plus 10X minus 50 equals 0. Now what we have to do is solve for X, which is a quadratic equation that does not have a simple two-root solution. So we're going to do some quadratic formula. 300 over 2. It's going to be 10 squared, which is 100, minus negative 200, which is going to be plus 200, which is going to be 300 there. So if we do negative 10 plus radical 300 over 2, we're going to get around 3.6. If we do 10 minus radical 300, well, negative 10 minus radical 300 divided by 2, we're going to get some negative number. And it doesn't make sense for us to have a negative number. So we're going to can't cross that one out. We're going to go with 3.6. And if we look back up, we'll see we have an answer B, which is 3.7, which is most nearly the what we got. So we go with answer B for that. Right? Not too bad, right? Just need to equate two E fields, do some E field calculations or algebra calculations for X, quadratic formula, and you got your answer. So unlike the previous session we did with economics, it might be a little more difficult to find an intuitive answer for some electricity magnetism problems, since it's a little more abstract topic compared to economics and ethics. So we might have to do a little more work to get our answers. All right. Moving on to our next problem. I have worked this one out already, but that's all right. We can do it again. I like to work out all the problems beforehand, so there's a quicker calculations, spend less time, get through more stuff, people more happy. All right. Let's change that. You're doing this again. Well, okay. So we have a current carrying a current of 10 amps flowing through 1 millimeter diameter wire. Okay, so let's draw our wire. One millimeter diameter. What is the average, most nearly the average number of electrons per second that pass through? Okay, so we want electrons per second pass through the cross section. All right, so maybe wondering what is the equation to get the average electrons per second? Well, that equation is going to be Q dot. So what we can do is we can go check our handbook really quickly. Let's look up electron density. No electron density. All right, let's look up what's a conductor? Conductor. Conductor, conductors, conductors, semiconductors. We want to go back to the electricity and magnetism section. Here we go. Okay, we're being asked for, what is it? What is the average electrons per second? Sorry, this is not a conductor. This is current carrying the wire. We can see if we can find the information we need. Current. Nope. Many instances of current. That's a lot of current. Okay. This would be under interesting. I wonder if it is in here. Another reason you probably want to go ahead and research the handbook beforehand is in case you come across a problem that you've seen where the equation is before. It might be easier for you to find it from there, if in case you don't remember it completely, which no one's expected to memorize every single equation that's in here. Electron wire. Oh, here we go. Maybe we have it. The charge of an electron, which is good to know. That's not what we're looking for. Well, maybe it is in there, maybe it isn't. But regardless, if you can't find it and you don't know how to continue, it's recommended to skip the problem at that point. But for this, I happen to know this equation, and it's simple. It's a simple one too, which is why it's a shame we couldn't find it easily. This might be an easy point if you just knew the equation is I over Q, the current, divided by the charge. If you think about electrons per second, current is amp and charge is coulombs, and you can get electrons per second if your charge is in electrons. Let's say this charge is in charge of an electron is at 1.6 times 10 to the negative 19, I believe. And that's electrons. So I mean, the answer for this obviously is, you know, as simple as this calculation here, which will get us 6.3 times 10 to the positive 19 electrons per second. Ten divided by that, this gets turned into positive 19. That gets moved. Yeah. So our answer would be D here. So not being able to find the is this the right screen? Yeah. The equation is a little bit saddening, but it shouldn't be the end of the world if you have to skip one problem and come back to it because you don't know the equation. Okay. Let us. This is another kind of quick one. Took my lasso away. Are we gonna do this again? Okay. There we go. Okay. We have a solid copper conductor at 20 degrees Celsius and has the following characteristics. We have the resistivity. Nope. We have resistivity, diameter, and a length. What is the resistance of the conductor? This is the one that I was looking up earlier. So we go to our handbook. You can see this correct. Cool. We can look up conductor now. Go through some of the choices. Magnetic fields, conductors, resistivity. For a conductor of length L, electrical resistivity rho, and cross-sectional area A, the resistance is, bam, right here. So R equals rho L over A. Let's go back. Resistivity equals rho L over A. And rho is the thermal resistivity, I believe. Oh, electrical resistivity, my bad. Yeah. Which we have that as here 1.77 times 10 to the negative 8. So we can have our equation look like this. Times 5,000 meters divided by diameter is that. So we can, if we want to do pi over 4 d squared, that's fine. Or you can do what I like to do pi r squared because that's feels safer to me. 0 points times 0.0025 squared. That'll give us what? Put that in your calculator. It'll get you around 4.5 ohms, which we have as the answer. Choice B here. Nice, right? Nice simple problem equation. You search up a conductor, and that was really all there was to it. There was an equation there for resistivity, and you're able to solve that. Nice. Okay, so those were some problems on electrostatics. Now we can start looking into some for DC circuits, which if you've taken a E&M class, you probably have seen quite a few of them. They can be kind of lengthy though. All right, let me erase these doodles here. This as well. No, not that too. Don't want to delete the problem. That's okay. Okay, that should be good enough. So we have a circuit here, and we're being asked to find the voltage going through the middle 5-volt resistor. Now, I don't understand how much of a journey it is to actually get that. What we have to do to get to that point is come up with, let's say we have this here, which is I1, I2 going this way, 2 loops, Kirchhoff's loop rule. We have to find both of these currents, because then we need to get that. They'll give us the current here in the middle. Then we do V equals IR, and then we can get the voltage drop, the voltage across. So the main point of this problem, or the hardest part of this problem, is to get the currents, because we're going to have to do a lot of equations. I'm going to make this a little smaller. Have some more room to work with. I will just redraw this. That's fine. All right. So based on Kirchhoff's loop rules, we know that if we go through this loop here, we can get an equation for the left side of the circuit. So we start with 10 volts, positive 10 volts. And we're going to drop by 5 ohms times I1. And then we're going to drop by 5 ohms again times I1 plus I2. And then it's going to equal 0, because we're going to be getting back to the source, which is 0 potential. Next one, we're going to start with 30 volts minus 5 ohms times I2 minus 5 ohms times I1 plus I2 equals 0. Again, we get back to 0 potential. Now we got to do some substitution here to get equations for I1 and I2. So we can have I1 on the top. Okay, let's color this. We need more colors. Orange, and we'll color the other one this magenta. So let's do this one first. That's not a -2. That, I'm not sure where that little bit came from. Okay. Let's solve for I1 on the top. We're going to have, let's put this -5 ohm I1 minus 5 ohm I1 as well. This is going to get distributed in, and we're going to move everything else to the other side. So -10 volts plus 5 ohms times I2. Okay. This is going to turn into, it's going to turn into a negative 10 divided by negative 10. So I1 turns 10 volts minus 5 ohms I2 divided by 10. All right. Now what we can do is either throw that into the 30, and let's throw it into the 30-volt equation. $30 minus 5 I2 minus 5 times 10 volts minus 5 ohms I2 divided by 10. Let's see what I was going to say. That's 5 I2. Oh yeah, minus another 5 times I2. I have everything in terms of I2. We can solve for I2 here and then plug that in for one of the other equations to get I1. Minus 10 I2 minus, what's this going to turn into? Simple way to do this. 5 times 1 volt minus 1/2 I2. But I do this incorrectly, that would be good. Equals 0. $30 volts minus 5. This is going to be in a current. Okay. 30 minus 5 plus 5/2 I2 minus 10 I2 equals 0. 25 minus, it's going to be 20 over 2 minus plus 5, so minus 15 over 2 I2. So I2 again, depending on the signs of everything, things could be negative or positive, where in turn they were not before. But we're going to have 50 over 15. That's correct. Which I guess simplifies to 10 over 3 amps, and that's I2. And now if we throw that into our equation for I1, that times 5, 50 over 3. Let's do a different color and also move this down a little bit. $10 minus 50 over 3 divided by 10, I think. Yeah, divided by 10. So I1, negative 20 over 3, 10, That gives us 20 over 30 equals negative 2/3. So now that we have those two, if we add them together, we can get the I in the middle. Is an 8 over 30 amp. And if we take that I mid times 5 ohms is the net resistor, we get voltage drop or voltage across, which is equal to 13 volts. 13.3 volts. So if we look at our answer choices, what do we got? 13 volts is choice A, so that would be our choice for the matter. Again, I'm going through these kind of slow so that I can show all steps, but typically you don't want to take more than 3 minutes per problem. So if you see this, you're like, all right, cool. 2 equations, 2 unknowns, solve simultaneously. If you know you can do that really quick, go ahead and you probably do it in like about 2-3 minutes. But if not, if you think it'll take a little longer, definitely skip the problem, come back to it. Especially since you know how to do it, you just have to know you have time to do it. These problems are a lot longer than others. Okay. Quickly check our Discord. All right, we got some people on here. That's good. All right, now we have a 20-volt source connected across terminals A and B with a current of 10 amps as measured through R. What would the flow be through R1 if a 30-volt source is connected to these terminals here? So they're saying if we connected these two together with a 30-volt source, what would the flow, current flow, we want I, right? V equals IR, so I equals V over R. But do we know what the resistance is? My bad, we are actually missing an entire step here. This actually tells us. Oh yes, that will be the case, but I think we need to find this resistance first. So when a 20-volt source is connected, let's get green. When a 20-volt source is connected, and then when a 30-volt source is connected. First, we do the 20-volt. When a 20-volt source is connected, the current of A is measured, or 10 amps is measured through R1. So we know that 10 equals 20 over R for the first case. And for the second one, we have I equals 30 over R. So if we get this R and this R, they should be the same. So this R, what do we do? 20 over 10. So green R is going to be 20 over 10, which is 2 ohm. Now we take that, put it in for the red R. We have I equals 30 over 2 ohm, which we have a current of 15 amps coming through when we put this 30-volt source here. Nice, so we go up 10 volts. Our current changed by 5 amps. which makes sense because the resistor is 2 ohms. Cool, huh? Nice, nice. That took us about 4 minutes. Probably could speed it up a little bit. But if you knew exactly how the relationship would work, if that was a 2 ohm resistor, you'd know that the current would go up by half of the voltage increase. So, little relation there. All right, I have more problems, but we're gonna take a little break so you guys can catch your breath. I'll get some water or something. I'll get a couple more problems on DC circuits. Or if you'd like to request something or have questions, that's welcome as well. Won't be getting into AC, or I mean, we could go into AC or rotating machines if you want. So I'd have to refer strictly off of the solution manual to figure out what's going on with that. Okay, be back in a second. All right, we're back. Got about 3 more problems here, and then we'll see if we have any questions, and if not, we'll end there. So if you guys some time, don't want to make this too long. All right, so got our next problem here, where this is still in the DC circuit section. If a current of 7 amps passes through a 12 ohm resistor, what is the power dissipated by the resistor? Well, we did go over these equations a little earlier, but let's go to let us go and find them actually. in our handbook? So we want power, right? Power. There's a lot of powers. Maybe we can make it a little more easy to find. What about we call it, let's look up resistor. A lot fewer of those, right? Well, look at that. We have it already. Power absorbed by a resistive element. P equals VI, V squared over R, or I squared R. So let's write V squared over R and I squared R. Power is equal to V squared over R, so also equals I squared R. Okay, we have a current, and a resistance, resistor. Well, it looks like we're going to be using this, huh? So 7 squared times 12. Ah, we're in horsepower, huh? All right, that's makes things a little less convenient. Let me go back here. Well, I guess I'm gonna have to go back anyway. But anyway, we have we would not get the correct units if we were to do this 7 squared times 12, which will give us what, 49 times 12, 588. That's not in the units we want. This needs to be converted to horsepower. So we're gonna let's go back and see if we can find a conversion factor to horsepower in the handbook. Horsepower. To obtain horsepower, multiply. We're currently in watts. Just watts, so we don't want a kilowatt conversion. Which one? I think that's what we're going to have. Let's see. Feet, pounds. There's watts. 1.341 times 10 to the negative 3. So we need the inverse of that. Well, or just multiply by that. Okay. So 1.341 times 10 to the negative 3. That is watts per HP. No, HP per watt, I think. So if we multiply 588 by this, our watts will cancel out. We'll just be left with horsepower. Which gives us about 0.788 HP. That's, which one? This one, huh? This one's closer. Answer choice C is what we select. That is correct. Good job. Cool thing at the end, yes, at the end of the handbook, you will have a bunch of conversion factors, which can be useful if they ask for something in a different unit. It shouldn't be too difficult to get to it. Okay. Now we have some converging currents. If you don't know what to do with converging currents, you must add them in the respective, it's almost like a vector in this case. So if you have 3 currents going in, my bad, not like a vector, but you must have Kirchhoff's law, where the sum of the currents in must be equal to the sum of the currents out. So 5, 10, and I. So what must I be? This one you can kind of look at and think, oh, A's got to be a negative current because 5 plus 10 is nowhere near 3. So I has to be on this one is kind of almost a given outright. Since there's only one negative answer, but if we were to humor ourselves, just basically like that, I is going to be negative 12 to balance that out. That one's pretty straightforward. Hope you get a question like this. That'd be nice, right? Okay. We have one more problem for ourselves here. Yeah. So we have a charge of about 0.75 coulombs passing through a wire for 15 seconds. It's nearly what is the current. We have a charge, and we have time. Charge per time. Moving charge. That's a current. Is it not derivative of charge with respect to time? Will give us a current. We're asking in milliamps. Okay. Well, if we just take this 0.75 charge divided by 15, let me write straight for once. So give us coulombs per second, which is amps. Isn't it? Okay, hopefully you can see the rates. You're seeing the rates. Yeah. What's this? 0.05 amp. Let me turn that to milliamps. 1, 2, 3 is about 50 milliamps. Is this correct? Yeah. Charge over time. If you know the nature of what current is, this one should also be kind of a given for you. There's one we can add some inductances. We've gone through most of the hard problems on here. Let's look at an AC circuit problem. Weirdest thing about the AC circuits is they have a lot of phase conditions, which is a little abstract. Most of the subject is abstract, but frequency of this circuit shown. Okay, let me look at this one then. I don't have an image of this one, but I can try it. So imagine we have a circuit. Capacitor here. Alternating current source. And we have an inductor. Here, this is going to be 4 henries and 3 microfarads. What is the resonant frequency? We want resonant frequency. And we get some answer choices. All right. Let's see first if we can find anything in our FE handbook. Let's look up some resonant frequency, see if that's a thing. Resonant. Oh, got 1 and 2. The radian resonant frequency, but both parallel series resonant situations is that. I think that is what we want. Let's look at the other one really quick again. Damped resonant frequency. This is control systems. No, this is not what we're looking for. The only other location for resonant in this entire handbook is here under resonance. So let's look at this equation. 1 over LC equals 2 pi frequency. Okay, Let's write that down. Okay. 1 over square root LC equals to 2 pi frequency 0, which is this omega 0. Check. Yeah, that's radians per second. All right, we have an L and a C. So technically, if we take L and C, 1 over LC times 1 over 2 pi, we should get our frequency. Yes, let's try that. 1 divided by the square root. That's in micro, so it's going to be 4 times 3 times 10 to the negative 6 times 1 over 2 pi. Right, because we divide this 2 pi over. It's going to be 1 over 2 pi times that, and that. Assuming that this F0 is what we are looking for. Root of that. 1 divided by that. It's about 288.67 divided by 2 pi. Which gives us about 45.9 radians per second. And radians per second, we can also consider that as hertz. So we can call this hertz as well. And if we look at our answer choices, 46 is a answer choice. That's answer choice C. So we can conclude that our answer is most likely answer choice C, even though we did not understand anything really about what the resonant frequency is. So it's another example saying you don't necessarily have to completely understand every topic on this test to its fullest extent. For this one, all we really did was look inside the manual, the handbook, for an equation that would get us what we needed. It was a question that was simple enough where we didn't really need to know too many rules and laws, which would take us too long to search for in the book. Let's say you wanted one of the previous problems that we did. You wanted to do this circuit here using Kirchhoff's law of the 2 loops. You wouldn't have, I don't think you'd really have enough time to research and learn what the loop rules were, and then do this simultaneous equation thing. I don't think there would have been enough time to do all that. But for something like this, where it's just a single equation that you need, the handbook is a great resource to just use, find it, use the equation, even if you don't understand where the stuff comes from. So that's one AC circuit problem. There are some AC circuit problems that you cannot easily figure out like that. It's interesting. A lot of these questions in here are asking for the frequency of the AC source frequency. Reactance. Okay. Rotating machines, another one. Actually, rotating machines literally only has, there's no real pictures, it's kind of just text ones, conceptual and non-conceptual. Well, I believe we've looked at enough today. I do not want to make this recording too long. If there are any questions and you are watching this in the future, please leave it at the comment section below. Myself or one of the other officers will do our best to get to that. And if you have a question and you're here currently, that's great. You can ask it, unmute yourself, or type in the chat. We have a chat here. Yes. Thank you, Sylvia, for being here. for the whole entire time. We'll be doing this. I'll be doing this. Might have some others come in, other officers come in and work through these with me as well. I know last time we had a couple come in and we're having fun going through the economic problems. But yeah, every Friday we'll be going through different topics. Next topic is actually going to be static, so we're finally going to be getting into more of the engineering stuff and the stuff that people might have more interest or more questions on. Though next week in particular is a break week, I will not be available. So there will be nothing next week, but the week after we will start statics and go from there. It's going to be fun.
Sounds good. I have a question. Do you have
Awesome.
any like
this will also be up on our YouTube channel for reference at later time.
Yeah.
And I hope that you everybody has a good experience taking this exam because it is a large exam.
Yeah, I just want to know if you have any recommendations for reference material.
Again, last call for any questions. I see your mic is unmuted, but I do not hear anything. Are you speaking? Chance.
Yeah. Oh, okay. Okay.
This is not. Yeah, I don't know if maybe I have my sound off or something. Yeah, if you have a question, sure, you can type. That's cool. Yes, reference material. There is a FE Mechanical Practice Problems book by Michael R. Lindenberg. What you're seeing on the screen are actual problems from that. His name is, so it's FE Mechanical Practice Problems. Michael R. Lindenberg. That's where I'm currently getting some of the problems referenced from. There's also courses you can take. They're a little bit more on the pricey side, but there's one by PPI 2Pass. PPI 2Pass. They offer some courses, which I think they also use the exact same book. That's one that I'm currently taking that right now, course with them, going through all of the stuff. They have quizzes that you can take, a whole library of problems for you to do. It's a lot. It's intimidating, but everything is scheduled out. Similar, basically the schedule that they have me doing for that course, I'm adapting into this in a similar format. Time-wise, not so much, but in terms of the topics that are tackled first, that's the same order. Most important ones being likely thermodynamics, fluid dynamics, which are ones that will take definitely a lot more time on. Whereas for Tau Beta Pi's workshop, we will only be spending a week on them. They will probably be sessions that end up going about 2 hours long, but we'll be getting through as much as we can after I've refreshed myself on the topic, so I can, actively and effectively tutor other people to help them remember what they need to remember. But other than that, yeah, if you don't have any further questions, thank you for joining this electricity and magnetism journey, one of my least favorite topics, to be honest, but there will be a couple questions out on the exam, so you got to remember some stuff for that anyway. No problem. All right. Take care, everybody who's watching. Sylvia, you as well. Thank you for joining. And hope to see you all again next week. Bye-bye.